Welcome. I am Steffen Zschaler, and in this video I talk about work done together with Fiona Polack, presenting our vision of how software language engineering can help us build better agent-based simulations. Let me start by briefly discussing what agent-based models are and why they are needed. Agent-based modeling is a specific form of computational modeling. Computational modeling allows us to experiment with systems where real experiments are too costly or dangerous. This is based on an in-computer representation of the part of reality of interest. This is an abstraction from reality. Results from computational modeling can then help guide real-world experiments to understand how true the abstraction was to reality. A specific type of computational modeling is simulation-based modeling. Here we execute the system's behavior inside the computer step by step. This can be very useful to help us understand the behavior of complex systems. Simulation-based models can be built in a number of different ways. One way is bottom-up modeling, where we focus on modeling small-scale behaviors inside the system and then simulate these at scale to see if they can explain a large-scale behavior that we are observing in reality. If this is the case, then we can say that the system behavior emerges from the small-scale behaviors. Agent-based modeling is one key technique for bottom-up modeling. Here we think of the system as consisting of lots of agents who have individual behaviors and interaction patterns. Depending on what we model, these agent behaviors can be fairly simplistic and almost robot-like, for example, guided by differential equations in some biology models, or they can incorporate models of higher-level intelligent behavior, like decision-making, beliefs, emotions, etc., where we model complex social interactions. Agent-based models are seeing increasing use in various domains, from modeling how cells coordinate in tissue growth to understanding social systems like urban traffic or COVID spread or patient flow. Agent-based models can be currently developed in one of two ways. On the one hand, there are some agent-based modeling platforms such as Repast or NetLogo, which provide agent-based concepts for programming ABMs more efficiently. These can be quite effective in developing agent-based models, but require stepping down to full programming as soon as the model requires more than the predefined types of behaviors. On the other hand, many agent-based models are developed using standard general-purpose languages. This provides great flexibility, but the obvious drawback is that one has to develop all aspects of the agent simulation from scratch. Let's look at how we think about agent-based models. On the one hand, we have domain experts who are interested in their domain but don't think the way a computer does. In fact, they will often not even think about agents or agent interaction. Their concepts are much more specific and focused on the problem at hand. On the other hand, computational models are built from variables, classes, objects, ticks, agents, etc. They need to worry about discretization of time and space, and they make abstractions from reality that needs to be documented. There is thus a mismatch between the way domain experts think about reality and the way this reality is represented in a computational model. Disparate languages like what we have just seen with domain experts and computational modeling are a problem because they make it difficult for domain experts to trust the model. Because the model implementation is so far away from their reality, how can they know the model is right? What do the model's results mean in reality, and where do I need to make a change in the model if my understanding of reality changes? Yes, of course, we can try and teach domain experts to think more like software engineers, and that may address some of these challenges, but actually this approach is missing the point. There is still a need for translation between the domain expert's knowledge and the computational encoding. All we're doing by teaching domain experts to become programmers is to move that translation from the heads of software engineers into the heads of domain experts. As it were, we're moving from bad translation but perfect code to great translation but bad code. Perhaps more importantly, computational models are thinking tools. Layers of mental translation that have to be kept in mind at all times severely limit the kind of systems we can understand with these models. The Cosmos project addressed some of these challenges by carefully differentiating different roles and artifacts in the process of ABM development. A domain expert has an understanding of her domain, which, together with modelers, is translated into a domain model. The latter is necessarily an abstraction of the domain, and ideally the ways in which it deviates from reality will be carefully documented. Software engineers then take over to translate the domain model into a platform model specific to a particular simulation platform. This may well be a GPL-based implementation. When simulations are run, a result model is produced. This is consciously called a model to emphasize that these results need to be interpreted by a domain expert to draw meaningful conclusions in the domain. All of these artifacts in Cosmos are tied together in a fitness for purpose argument, explaining why the team believe that the model and simulation developed are an adequate representation of reality and that the conclusions drawn are justified. All of this within a given research context. Cosmos doesn't dictate the use of any formal languages for any of the steps involved, though informal variants of some languages are typically used for specific steps. As a result, creating a fitness for purpose argument is possible, but maintaining and fully validating it become much more challenging tasks. We believe that using domain-specific languages can improve the situation by explicitly linking all parts of the overall fitness for purpose argument. Our vision extends the overall Cosmos process with specific models and languages for each step. We begin with the idea that the domain expert has an understanding of the domain which is translated into a hypothesis model consisting of an actual domain model and some domain model queries. The former model, the actual domain model, captures the known and hypothesized mechanisms in the domain, while the latter, the domain model queries, capture established system scale behavior that the model should be able to replicate to be considered valid. As in Cosmos, all modeling happens because we have a particular research goal working in a particular research context. In addition to replicating some observable behaviors, we may wish to use the agent-based model to predict system-level behaviors. This is captured at the level of the fitness for purpose argument, which may introduce additional domain model queries, for example, to undertake sensitivity analysis. To actually run a simulation, we must first generate an executable implementation. As I will explain in a moment, we consider this should be done in stages. Similarly, domain model queries must be translated into simulation experiments, which may involve determining the number of simulation runs to evaluate to achieve statistical significance of results in the presence of aleatory uncertainty in the model. Finally, results from the simulation experiment must be back-translated into domain-level result models, which can then be referenced from the fitness for purpose argument model, for example, to demonstrate that the model accurately replicates real-world observations. These models all require dedicated domain-specific modeling languages. We envisioned that these languages would need to exist at least 3 different abstraction levels, from top to bottom, from the domain level, representing the understanding of the domain expert, to the agent level in the middle, that captures models in terms of agents, behaviors, and interactions, and finally, at the bottom, to the simulation level, which captures the specific technical implementation details of a simulation. Equally, we expect that there would have to be at least 3 types of languages for domain modeling, from left to right, for domain modeling on the left hand, query expressions in the middle, and result capture on the right. However, we believe that these languages could be built from modular language components, for example, to deal with particular recurring subdomains. Our envisioned approach offers a number of benefits. In particular, the classic benefit of separation of concerns that DSLs already bring also applies here. Software engineers, modelers, and domain experts would be empowered to contribute their respective expertise and combine them in the architecture provided by the DSLs. Encoding model implementation as transformations moves this aspect of the model out of people's heads and makes it inspectable, analyzable, and possible to challenge. This will improve the rigor and reliability of agent-based models. I've already mentioned the possibility of automatically accounting for some uncertainty by integrating support for statistical significance analysis in the model compilation. This could, for example, build on existing tools like Spartan or MC2 maps. We are proposing a vision that is built on incremental transformation rather than a one-step compilation, and this offers additional benefits, as lower-level transformation steps are likely to be reusable across many domains. As a result, they do not need to be re-inspected every time a fitness for purpose argument is constructed. Instead, we can reuse the validation effort performed previously. Thus, we can focus our efforts on smaller steps in the translation process, making it more feasible to provide reliable assessments. Our vision, of course, also opens a range of research challenges. Fundamentally, we need to work in specific domains to identify the concepts our DSLs should have so that they balance flexibility and expressive power in the right way. This is fundamentally the challenge underlying the design of any good DSL, and as a community we are beginning to understand the challenges and techniques involved. However, there are a number of specific challenges underpinning this general challenge. We need empirical work to understand how domain experts think about their domain and how they express and understand it. We need to then link these concepts to general concepts from the agent-based modeling. It would be good to identify subdomains and build catalogs of reusable model components. We also need to build a modeling language for capturing fitness for purpose arguments. While some ideas exist what such a language could look like, turning them into a usable language will be a challenge that goes beyond the challenges involved in building domain or query DSLs. There are also some challenges in simulation engineering, although these have been looked at to some degree by the simulation community. Thank you for your attention. If you have any questions, you can ask them during the conference Q&A, or you can contact us using the email addresses shown here.